for all of these. When you're looking at a synthesis problem, these are nice. You have the starting material and the product. That's not always life in the lab. For example, if you're in the lab, your professor might say, I want you to make this compound for me. You don't have the starting material. You have to figure out where to start. So you have the starting material and the product. You know where you're going. So for synthesis, the easiest thing is to figure out what's different between your starting material and your product, because that's going to get you from point A to point B. At this point, we haven't talked about any way to form a new carbon-carbon bond until today, and that won't be in any of this synthesis. So this is the first question you should always ask: is my carbon skeleton the same? And for all of these, it will be, because, again, we haven't learned any way to form a new carbon-carbon bond. But as the first question you should always ask yourself, is the main carbon skeleton the same? Do we have the same amount of carbons in our starting material and our final product? And for all of these, that'll be generally yes. And the other thing that's really helpful is to find where your carbons are in your starting material and your product. And numbering and highlighting can really help with this. So we see our starting material has the same amount of carbons, and we have a 6-membered ring with a CH3 group on carbon 1. That's true for both our starting material and our product. So where's our differences? Our differences are in carbon 1, we have an alcohol, and the starting material and the product, our alcohol is in carbon 2. Nothing changed on our CH3 group, is still on carbon 1, though you should know that we do have our CH3 group coming forward, whereas there's no stereochemistry in our starting material. So that is important to note for our stereochemistry. So our main difference is our alcohol looks like it moved from carbon 1 to carbon 2. We know there's no reagent that's just going to move an alcohol. And we don't have any functionality in carbon 2 in our starting material. So our key is to get functionality in that position. And most of these are going to be very similar, going through eliminations and additions, but later on we're going to be doing a lot more reactions, so we're going to have a lot more things that are going to be happening. The main way we can get a functional group on carbon 2 is through an elimination, where we have a pi bond between carbon 1 and carbon 2. And we know we have a route to do that. Once we do have a pi bond there, we have functionality on carbon 2, and then we can do an addition reaction to get to our final product. So we see that we have a route to do that. So now all we really have to do is put in our reagents. Note, there won't always be one route to this. There's best routes, and there might be multiple ways we can do this. So for this example, we have a fairly symmetric 6-membered ring, and whether we end up with a pi bond between carbons 1 and 6 or carbons 1 and 2, it's going to be the same compound. I'm showing it between 1 and 2, but it would be no difference if it's a bond between 1 and 6. So we could, in this case, because it's so symmetric, use our acid catalyzed dehydration, which is just our E1 elimination. And that's perfectly fine. The alcohol is not a good leaving group, but if we use our concentrated H2SO4 and heat, we can get the E1 elimination. Conversely, if we want to go through E2, which is a route we can also go through, we have to make our alcohol a good leaving group using a tosylate. So our TS chloride with pyridine. And that makes it a good leaving group. And then we can do our E2 elimination, and we want our most substituted double bond. So our most substitutive double bond would be a smaller, strong base. Both routes would work, but if you're going through the E2, you have to show using the tosylates of the alcohol group. In this case, our acids making our alcohol of the group. A lot of cases, this E1 route won't be good because we get rearrangements and we only can form the most substituted double bond. So unless we have a lot of symmetry, that route's not usually useful. But in this case, it's okay. And remember, E1 will never favor our most substituted double bond. Only gonna, never favor our least substituted double bond. It only ever favors our most substituted. So now that we have our reagents here, now we just need our reagents to go from here to here in this addition. So the question is, what did we add? And we added an alcohol, but we also added a hydrogen. It's not being shown, but we know we added a hydrogen. So we added H and OH across our pi bond. Now we have two ways, well, three methods of adding H and OH, but the question is, where did we add it? Did we add Markovnikov or anti-Markovnikov? Where is our alcohol? It's anti-Markovnikov. It's on the least substituted. We only talked about one way to do that, and that way does lead to syn addition, so that makes sense. So that one way is using our BH3. And THF, that puts our boron on our least substituted and adds the hydrogen on our most substituted. And they add it to the same side, followed by our peroxide and sodium hydroxide, which is where our OH comes from. And it's just going to take the place of the boron. So we need that part, otherwise our final product is going to have boron. So that's our anti-Markovnikov. For Markovnikov, we talked about two different reagents. If we don't want any carbocation rearrangement, if there's a possibility for it, then we want to use our mercuration acetate demercuration for that one. So that's how we go about doing these. And again, the first thing you always look for is your carbon skeleton. Is it the same? So any questions with that one? Oh, for BH3THF? Sometimes the book doesn't, I've noticed, but I want you to because really the peroxide can cause problems. So this one isn't as much of an issue as some of the other ones we talked about, like what we were talking about today with our NH2- and water. That will absolutely react. But sometimes peroxide makes things do weird things, so it's good to put that separate. But sometimes I find the book doesn't number one and two. I'm not as strict with this one because it's not as strict to the reaction. You would just get a cleaner reaction. And when you're in the lab, it's called optimizing. You'll learn how to optimize reactions to get the best yield and the cleanest yield possible. Any other questions?
What can happen when you add peroxide?
Peroxide does a bunch of different things. We're going to look at radical reactions in chapter 11, and we'll be seeing, and we don't want any competing radical reactions here. So it's good to kind of keep that till later. And we'll be really focusing on some of the reactions of things like peroxide do with radicals, and we'll look at radical reactions with pi bonds and things like that, so we're just trying to keep that from happening by adding it second. Once our pi bonds are already not there, it'll make it a cleaner reaction. And we will be looking at our reaction of H2O and peroxide, so we'll really see what peroxide does in the presence of a double bond. We'll look at that in chapter 11 in a lot more detail. Right now we haven't really talked about radicals, so it just does adverse reactions right now is what I can tell you. When we talk about it, you'll see. So in the next example, again, first thing I want to do is figure out where my carbon skeleton is and what's changing. Sometimes it's really easy to tell But notice how I have this drawn the same. Remember, our molecules can flip in space. I don't have to draw this in the same orientation. It happens to be drawn in the same orientation, but I could flip this whole molecule over. It won't change the synthesis. So it's always good to figure out where your molecules look alike in the starting material and final product. I like to highlight. I do that often when I'm teaching, and numbering is really helpful as well. So what we see is we have the same general carbon backbone in both our starting material and our final product. And what we see is that nothing changed with this carbon skeleton other than our bromine was in carbon 2 and now it's on carbon 1. But carbon 4 still has these two substituents. Carbon 2 still has the one substituent. So we don't see any big change there. Later on we will see changes to the carbon skeleton. So it's good to get used to seeing it now while we won't have any. So our main difference is bromine was on carbon 3 and now bromine's on carbon 1. So this just won't be one quick elimination and then addition. We're actually going to have to do multiple eliminations and additions to get to our final product. Otherwise, we can't just jump from having reactivity here to having reactivity on carbon 1. So right now, there's no reactivity on carbon 2 or carbon 1. And we have to basically move our bromine all the way to carbon 1. Remember, our hydrogen that we are deprotonating to form a double bond has to come from a beta carbon. Carbon 4 doesn't have a hydrogen, but carbon 2 does, so we can form a double bond between carbon 2 and carbon 3. And it's really important. Notice I'm not losing any of my other carbons in my backbone. When you're drawing these, you have to draw them looking correctly. If I didn't draw one of my CH3 groups, that would be incorrect because nothing's removing that CH3 group. It's still there. Now I have reactivity at carbon 2, so now I can put some sort of reactive group on carbon 2. Because we're working with bromine, we can just do another bromine addition of H and Br. But it doesn't necessarily have to be bromine, it could have been H and Cl. Could be H and OH, but remember OH isn't a great leaving group, so then you have to do extra work to make it a good leaving group. Now we still don't have our bromine in the correct position. We want it on carbon 1. So we're going to have to do another elimination. To now have our double bond between carbons 1 and 2. Also note, I could have a double bond between carbon 1, between this carbon and carbon 2, and that leaves us the same product. So now that we have functionality on carbon 1, now we can do another addition to add an H and a Br. And in this case, stereochemistry is not denoted, so we're just going to assume that we have a mixture. So now we just have to put in our reagents to accomplish this. If we look at having our carbon 3 bromine leave and forming a pi bond, this is definitely a case where you don't want to go through D1 because you will get a rearrangement, and a rearrangement will not lead to your final product. Because this would be a secondary carbocation, and we could have a hydride shift to get a tertiary carbocation or a methyl shift to get a tertiary carbocation. You'd probably get both, you'd get a big mixture, it'd be nice. So this one has to go through D2. Or want our most substituted double bond? Well, technically, our only possibility is double bond between carbons 2 and 3 because we don't have a hydrogen on carbon 4. So it really doesn't matter how smaller big the base is, but the bigger the base, the slower the reaction. Because we do have some sterics on this carbon too, where we're trying to deprotonate our hydrogen. So a smaller base would be a little bit better there. It needs to be strong. You can denote that by putting your sodium or actually showing your negative charge. There's always a sodium somewhere. Yeah?
Can we put like NaO or EtO?
No.
Like once.
Oh yeah, you can do that. As long as you're showing your either counter ion or your charge. But yeah, you can put ET or Me. And either of those would be fine. You can shorten it as long as it's clear what it is. So now that we have our reagents to form that intermediate isolatable compound, now we want to take that double bond between 2 and 3 and add a bromine and a hydrogen across that pi bond. So our bromine is adding in the most substituted position. That's going to be Markovnikov. So we can accomplish that by adding HBr. Now to get our functionality between carbons 1 and 2. Now we do have 2 beta hydrogens. We have this one and we have 3 on this position. We also have 3 in this position. But again, if we deprotonate here or here, that's going to lead to the same compound. We have 3 rotations around this single bond. So we have a difference between this 1, 2, 3 tri-substituted double bond, or the double bond we're trying to get is only di-substituted. So that's going to be our least substituted double bond. We have to go through our E2 reaction for that. But here we need a big, strong base. It won't show the negative charge where I want it. There we go. And that will form our least substituted double bond for our E2 reaction. Yep.
Again, I've been on the in the book. I've been using like TBU. Okay.
Yeah, that's just the same thing.
Just writing things.
Yeah. That's fine. The potassium is just your counter ion. If you just put TBUO as tert-butyl oxide, then you have to put the negative charge. But it's okay as long as it's clear. And the last step, we're adding another H and Br, but this time our bromine is adding on carbon 1. So that's our anti-Markovnikov. So now we need the presence of peroxide. And we're going to look at that mechanism in a lot of detail in the next chapter. Right now you don't know the mechanism. And remember, this particular step only works with HBr. So we could have used HCl here, that's fine, doesn't matter. Could have used HI here, it's fine, so but here we have to use HBr if we want it to be anti-Markovnikov. And in the next chapter, we're going to really look into the thermodynamics to understand why this only works with HBr and not the other halogens. Any questions? In this example, and the other examples we started with leaving groups, in this example it looks like we're just moving a pi bond. Well, we're going to be going through the same types of reactions because again, we only really learned so many reactions in this particular chapter. But repetitiveness is good when you're first starting. So, I look like I'm moving. And my numbering is just for me. Again, there's no difference in my carbon skeleton. That's pretty clear. There's no extra carbons from my starting material to my final product. But it looks like we're moving our pi bond from between carbons 1 and 2, which again, this numbering is not for naming. It's just for me to talk about it, for you to see what I'm doing. So this is arbitrary. So it looks like we're moving our pi bond from between carbons 1 and 2 to between carbons 3. Clearly, we don't have any route to do that right now. So, what's going to be our first step? Yes. We're going to do an addition. What should we add? Halogen's probably the best. Again, we could technically do an alcohol, but then the alcohol is not a good leaving group. And then, of course, we're also adding a hydrogen. Just as a side note, we are adding H and Br. And I'm just showing it there so you can be clear. Well, if we look at our starting material, we only have 2 hydrogens on this carbon, and now we have 3. So we had to have added 1. I'm just showing the one that we added. Came from our outside source. So, how do we do that? What reagents do we use? HBr, and it's Markovnikov, so we don't have to add anything else. Of course, there's some sort of solvent, but this is undergoing through HBr. Okay, in the next step, now we have a leaving group on carbon 2. So now what's our next step? An elimination. And where do we want our pi bond? Between 2 and 3. Or technically between 2 and that other one because it's the same compound. It's very symmetric. And when we're looking at that to put in our reagent, our options are forming, we have a leaving group here. If we form the pi bond between the least substituted, that would reform our starting material. But we're trying to form a pi bond between the most substituted. So what reagent will we need for that? A small, strong base. Ethyl, methyl, either one. It must be strong. So now we have functionality between carbons 2 and 3. Now what's going to be our next step? Another addition. And where are we adding our halogen? Carbon 3. So that means our hydrogen must add it on carbon 2. So now, of course, we're doing that with HBr, but what else do we need? We need our peroxide, because that's anti-Markovnikov. Because our carbon 3 is our least substituted compared between 2 and 3. So now we can get to our last step, and what's our last step? An elimination. And we want our pi bond between 3 and 4, of course. So what kind of base do we need? What should it look like? A big one, because of course this is our least substituted. So that's our mechanism. Notice all of these compounds are isolatable. They're all neutral. These are not mechanisms. Each of these steps has its own separate mechanism. If I want you to draw a mechanism, you could draw it for each of these steps. But I'm not asking for a mechanism if I'm asking for a synthetic scheme. Now this seems so easy. When you get in lab, you'll see that each of these steps might take you a day, might take you hours, might take you days, might take you a month to do. But it's still getting you on the path. You're basically mapping out your path of your reaction. So that's what we're trying to do with these. Here's another pretty similar one. Again, at this point, we're still pretty repetitive. But if you started playing around with Chapter 10's synthesis problems, which I'll probably do a review on Friday next week of, because I'm super busy with all the things that have been going on. If you look at Chapter 10's, it's getting a little bit more complicated because we're actually changing the carbon backbone. Because we have a reaction where we can actually form a new carbon-carbon bond. And we started looking at reacting pi bonds, taking a triple bond to a double bond. So we have more things going on in the reaction. And we'll have a bit more to talk about, which is why I didn't want to just wait and have synthesis practice of all the chapters. It's a lot, and then I'd be here talking forever. So, it still seems pretty repetitive, and the more you play with, you will see it can be repetitive. And that's good, because that gets you used to how you're doing it. So when it comes more complicated, you know how to work with these. So first off, we see that our carbon skeleton is the same, which is going to be true for all of these. We haven't learned how to form a new carbon-carbon bond yet, but it's always good to pay attention to it. So what we see is on carbon 2 we have a CH3 group, and we do in the final product. So all of our carbons are in the same position, they have the same connectivity. Our difference is we had functionality on carbon 2, we have an alcohol, but in our final product we have functionality between carbons 3 and 4 in the form of a double bond. Clearly we're going to go through some eliminations and additions again. First off though, we don't want to go through, it's probably not useful to go through an E1 for this particular one to do an elimination, just because we are now getting a possibility that we have not very much symmetry, and we might get byproducts. This one still might go through an E1 okay, because there's really no rearrangements that can occur. That carbocation would be tertiary. And we are trying to get our double bond between 2 and 3, because that's getting us closer to 3 and 4. So that is our most substituted. But just to be really clear, let's just go through E2 to make sure we don't have any adverse reactions. So our first step is going to tosylate our alcohol to make it a good leaving group. And I'm going to show this as 2 separate reactions, though a lot of times in your book you'll just have a number 1 and then TSCO and pyridine, and then a number 2, your base to make it a good leaving group. So to be really clear, I'm showing, because you will have to isolate that compound in between when you're doing that, but often the book will group it together. You do need a 1 and 2 here, because if you react tosylchloride with your big strong base or small strong base, it's just going to react with the tosylchloride, because the chlorine's a really good leaving group. So we want our tosylchloride to react with our alcohol. And especially when you first start out, I really want you showing all steps clearly, just so you can follow it when you're studying as well. And when I'm grading, I can write little notes a lot more clear if you're showing your steps clear. And I try to in your quizzes, I try to write you notes for you to see where you're doing wrong. Though every once in a while, if you put 5 bonds to carbon, I might just put a big note on your page with a lot of exclamation points. I have been known to do that. No 5 bonds to carbon. If I see 6 bonds to carbon, that might have 2 O's. No, don't do it. So oftentimes though, that's because you're not following your hydrogens. And I just drew this, and I drew this angle really in. You really should try not to draw your angles too off. So I'm going to subtract that, because remember, it's a tetrahedral angle, and we usually try to draw our skeletal structure with the angles as close to what they should be as possible. So just trying to be neat when you're doing these. I have a disadvantage that this technology system, sometimes I touch in a certain place and it's not quite drawing in that place. But try to be neat. It's really important, because the difference between being neat and not being neat might make me think that you're showing an extra bond when you're not, or something along those lines, because it is a symbol that you're drawing and I'm reading it like a different language. So now we want our elimination. We can use our E2 because now we made our alcohol a good leaving group. And we want the most substituted double bond. So again, like we've been doing, we can use our small strong base. That'll give us our double bond between 2 and 3. Of course, we want it between 3 and 4. So we can do a what? It's our next step. An addition. And again, because alcohol is not a good leaving group, just better to do your BR. And we have to use HBr in this case, because we want our bromine to be anti. So that'll be using our peroxide, because carbon 3 is our least substituted. now we can do our last step, which is our elimination. And of course, in this case, to get our double bond between 3 and 4, we would need a big, strong base. So we get our least substituted double bond as our highest yield. And bromine's a good leaving group, so we don't need to worry about calculating anything.
Or you use a strong base, you said?
You always have to use a strong base for E2. Go back, review chapter 8 about what we need for elimination versus E1 versus E2. We need a strong base to promote E2, and we use our acid catalyzed reaction to promote E1 and heat. Heat helps with any elimination to promote that over substitution. Yep. Oh, that is an S. That's not an M. OTMS is a different thing. We will learn about it in chapter 13. That is incorrect. It is an S. Sometimes when I'm talking and I'm writing, I don't always write because I'm talking ahead of where I'm writing. We will learn TMS, and that is a different kind of group. It is actually a protecting group. It doesn't make alcohol a good leaving group. It protects it from reaction. So it is TS. Also notice it's TS fluoride, not OTS fluoride. The oxygen is because this attacks our molecule in chlorine's leaving group. So this first step is a SN2 reaction on a sulfur instead of a carbon center. So the oxygen is this oxygen. So don't accidentally put OT. And if you want to revisit what your calcium chloride looks like and why it makes alcohol a good leaving group, revisit chapter 7. We could also use a couple of, like, tosylate are most common. Triflate's another good one, but triflate is very reactive, and in the past when I've used triflate, you buy it, it comes in a little vial, and once you open the vial, if you don't use it all, it just decomposes. So it's a waste of money. Tosylate works well. Stays in the lab for a long time. Tosyl chloride. Kind of smells bad though. I don't like the way tosyl chloride smells. Give me a headache. Okay, so this is the only one that's not addition and elimination for this example. So first off, the main carbon backbone is the same, which is our 5-membered ring with a CH3 group on carbon 2. Carbon 3. However, we do have a new carbon bond. It's a carbon-oxygen bond. And we have new carbons, but it's come from being stuck to an oxygen. So we are losing bromine, and something is taking its place. What reaction is that? Substitution. But we only want to get the stereos. So this is not just a simple SN1 or SN2. First off, why is this not just a simple SN2? What stereochemical controls will we get with an SN2 reaction? The SN2 mechanism is conserved. Our nucleophile attacks while our leaving group is leaving. What does that do to the stereo center? Inverse. Is that stereo center in our product inverse? No, it's the same. This isn't a simple SN1. Why? What does SN1 do for our stereo center? Oh, but I only want one. So if we go through an SN1, the most I can ask for is 50% yield. Instead, what can I do? Well, if we do an elimination, remember we're always going to, first off, there's a couple of problems with doing an elimination. One problem is, let's say we do an elimination. All right. If we add something to it, will we be adding, let's say we throw HBr in this, will we add Markovnikov or anti? Which carbon is more substituted? Neither. So we have no regiochemistry control. We add an HBr, we'll get a mixture of compounds, a bromine on the carbon where our bromine was, and a bromine on carbon 2. So in this case, substitution, an elimination isn't going to get us too far. Because that pi bond, we lose all control with it. It's neither more substituted or less substituted. We'll get a mixture of any addition, except for if we're doing hydrogenation, then we'll get one compound. Otherwise, we're going to get a big mixture. So that's not useful. But it's always good. You can draw it out. Think about why it wouldn't work. Also, we really didn't talk about a way, well, the addition with that would be, we could do the mercuration. We could do that, because our alcohol is our nucleophile, so it would attach a hydrogen and an OH. It would, though, have our nucleophile and we'll substitute it. We don't have any control for that. Also, remember, we really don't have too much stereochemical control either. We're going to get both of the antigens if we get a stereocenter. So in both ways, even though we'll get some of this product, but we'll get a lot of other products. We'll probably get both of these plus both stereochemistries of this one plus both stereochemistries where our ethanol attacked carbon 2, because we don't have any control with this reaction. So that's not a good route. It's a route. You'll get some of it, but it's not a good route. How about we force an SN2 reaction, and then we force a second SN2 reaction, and we force one more SN2 reaction, say iodine, we'll get all the inversion product. Now iodine's in there. I'm using DMF because remember for SN2 we want a polar aprotic solvent. That's DMF. We talked about those in chapter 7. So I can force a second SN2 reaction. What is my nucleophile for my second SN2 reaction? It's going to lead to my final product. Say it louder. Ethoxide. When you have a negative charge on an oxygen, it's ethoxide. Not ethyl, but it's close. Now we will have still some issues, but this is the best route. The main issue is we have to be really careful to not get elimination. So we don't want to heat this too much because heating will favor elimination, as it is secondary. But as far as our stereochemical control, now this will attack and we'll get the inversion product. So it's not to say it's completely no problems free. There's some chemical reactions that are very little problems free. But most of the time, if you're in organic synthesis, if you're a chemist, you're trying to make a new drug, you'll likely encounter some problems. And you just have to work with your route and optimize to try to get your final product to be in the highest yield possible with the least amount of byproducts. Sometimes it's unavoidable. We're trying to make compounds do things, but we can only make them do so much based on what nature wants them to do, which is be in their lowest energy state possible. So with high pressure and high temperature, we can sometimes get things to happen. Sometimes too high temperature, it starts decomposing. So we're always trying to work with what nature allows us to do and push the boundaries and optimize with what we can do in lab. And when you start taking lab, who's in lab now? So when you're in lab now, if you're taking lab, you get, here's your follow this procedure. But really, that procedure came about because someone worked with this amount of solvent, so I didn't have a good yield, changed the solvent, played around with it until it was the best at what you're working with. And that's what an organic chemist will often have to do. And grad school, I did a reaction, I think it came out to about 50 times until I finally got it to where I wanted it with all my temperature and my solvent system to where I got the most yield and I was satisfied with how clean the product was. So sometimes that's something you have to do. So that's it for this synthesis practice. And keep on practicing.